Hello, viewers. Waiting for everyone to hop in. Wait until we have 15 concurrent viewers and then I'll get started. Hello. She changed it. It's not in Kyoto anymore. Hello. Yes, physics time. Comes after computer science time. Hmm. I'm kind of tired today. I stayed up too late last night. But I'm happy that the air quality appears to be getting better. I think I'm going to actually go out for a run today instead of doing the stationary bike, which I've been doing for the past week. No, I say sleep is for the wheel. Uh, no, I stayed up late because I went to a. Uh, so I have a friend who works at a company um, that does COVID tests, and the employees actually get tested twice per day. They get tested in the when they walk into work and when they leave work, they get tested, and so because they're being tested so often, they can have get-togethers because they will know immediately if someone gets a positive test. So I went to a gathering with employees of this company last night. And I was probably there until I probably got back at about 11, and then I went to sleep at 12:30 or something. So stayed up too late. This company does a spit test. So you basically hawk a loogie into a little container, and that's how they test you. It's not the nasal swab thing. All right. I think I've got enough viewers to get started, so I will transition to the document camera. All right. So for the past few lessons, here's what we've done. We did a lesson with vectors. Then we did a lesson with defining position vector, velocity vector, acceleration vector. Then we did a lesson with the kinematics equations. And today we're going to do a lesson talking about what's called projectile motion. So that's going to be the topic of today's lesson, is projectile motion. Projectile motion, just to remind you, is two-dimensional motion under the influence of gravity. Okay, so we might have a situation that is like this. You've got maybe some cliff, and you got a projectile that is launched. Okay. And the projectile is launched at an angle, and it undergoes a two-dimensional flight path and lands somewhere over here. Okay. This is the initial velocity vector. The initial velocity vector will not be the final velocity vector because gravity is going to curve the path of this trajectory, so the direction it's heading is changing. Gravity is also going to slow it down if it's going upward, and it's going to speed it up if it's going downward. So the velocity is not constant. But let's just focus on the initial velocity, okay? So the initial, if this is the initial velocity vector, the initial velocity vector, we can make a triangle out of that. So the initial velocity vector is made up out of some of the velocity is going vertically and some of the velocity is going horizontally, okay? So we have to give the angle of launch, okay? And so the vertical component of the initial velocity I will call v y naught. And numerically, it is equal to v naught sine theta. Okay. Why is that? Well, here's the angle right here, and vy naught is on the opposite side from that angle. So the trig function that has opposite in it is the sine function. Okay. So v naught is the hypotenuse, it's the speed. So we can use those to get the initial vertical velocity. The x naught is the initial horizontal velocity, okay? So x for horizontal, 0 for initial. And that is equal to v naught cosine of theta. Where does that come from? It comes from the fact that this is adjacent to the angle, all right? So given a specific example, let's just do a specific example here. So what if we had a launch speed of 100 meters per second? And let's say it's at an angle of 40 degrees above the horizontal. Okay. So if I wanted the vertical component of that initial velocity, I would do 100 sine of 40. Just plug into my calculator here. That gives 64.3. We'll just call it 64 meters per second. And then doing the horizontal component, that would be 100 cosine of 40. You want to make sure you're in degree mode here. And that gives me about 77 meters per second. Okay? So that's how you get the initial vertical velocity and the initial horizontal velocity. So because this is two-dimensional motion, we have an x of t, and we have a y of t. Okay? And the formula for, I'm going to start out with the y of t. So the formula for y of t is y naught plus, so y naught is the initial elevation, plus v y naught times time minus 1/2 gt squared. Okay, g is the acceleration due to gravity. And that is equal to 10 meters per second squared. Actually, it's 9.8 meters per second squared, but for all of the problems in this class, you will round 9.8 meters per second squared to 10, okay? So this describes the elevation of the projectile as a function of time, okay? The x of t describes how far horizontally the projectile has moved as a function of time, okay? So this is x naught plus v x naught times time. So notice how both of these are just copies of that first kinematics equation that we derived a couple classes ago. Okay. One major difference, though, is that the y equation has a t squared term. The x equation has no t squared term. So why is that? That's because the t squared term is where the acceleration comes in, and gravity makes something accelerate vertically, but it doesn't make something accelerate horizontally. So we have no t squared term for the x of t equation. All right? So I taught you these equations last year, if you took my class last year. So we're going to focus on examples this year that are more complicated, okay? So let me write up my example here. So we've got two projectiles. Here's a cliff. All right. The cliff is 80 meters high. Cliff is 80 meters high. And there's a projectile that is launched from the top of the cliff. This projectile is launched horizontally at 90 meters per second. That's the initial speed of the launch, okay? It won't be the final speed because gravity is going to curve that trajectory and accelerate it. So its initial launch speed is 90, and then it's going to undergo a path like this. At the base of the cliff, or the base of the cliff, there's another projectile that is launched at 100 meters per second at an angle of 40 degrees. So it's exactly the same number as here. I'm just lazy, so I just chose the same number. Okay. And this projectile is going to undergo its arc. Maybe it's going to do something like that. Okay. The projectiles are launched at the same time. So my question is, how far apart are the projectiles after 1 second? So 1 second after the launch, how far apart are these two projectiles? So to answer this question, we are going to need an x of t and a y of t for each of these projectiles. So projectile 1, projectile 2. Okay. And notice how our x of t and our y of t have to do with initial positions. So when we're defining an initial position, we have to say where the origin is. So the origin, I'm going to say, is right here at the base of the cliff. That's where 0, 0 is. All right. So, and I will call this projectile 1, and I will call this projectile 2. All right. So projectile 1 starts at the origin. So its x naught is 0, and its Vx naught, its initial horizontal velocity, is 77 meters per second. So this projectile 1 has an x of t given by 77 t. All right. What is the y of t of this projectile? Well, its y naught is 0 because it starts at the origin. Its Vy naught is put a bar here so we separate those. Its Vy naught is 64 meters per second. So we have 64 t. And then we have minus 1/2 gt squared. So g is 10 meters per second squared. By the way, that's negative because gravity curves the trajectory downward. So we have minus 1/2 gt squared 10 over 2 is 5, so we have minus 5t squared. So that's the x of t and the y of t of this first projectile. Now let's do the second projectile. So the second projectile has hang on a second. I sense that dogs are doing something they're not supposed to be doing. All right. So now I need the x of t and the y of t of the second projectile. The second projectile starts directly above the first projectile. Okay, so it has an x coordinate of 0 initially. Okay, and its initial x velocity is 90 meters per second. Why is that? Because 90, if you have a horizontal launch, all of your initial speed is going into that horizontal velocity. All right. For the y of t, the initial y is not 0. The initial y is 80 meters up in the air. So y naught is 80. Vy naught is 0. Because if you launch something horizontally, none of that velocity is going up or down to start with. So we don't have the second term, and then all we have is the first term and the last term. So 80 minus 5t squared. Okay? So now what we want to do is we want to figure out what are the positions at 1 second, because I'm trying to figure out how far apart they are after 1 second. Okay? So I'm going to plug in 1 second here into these equations. All right? So if I plug in 1 second, the first projectile is going to be 77I. And then if I plug in 1 here, that would give me what? 59. 59J. So plus 59J. So that's the position of the first projectile. The second projectile's position at 1 second. I'm going to plug in 1 into both of these equations. So I have 90I minus 75J. Or plus 75J, excuse me. So we have that. So what is going to be the vector that represents the separation between these two projectiles? Well, we have to subtract the two vectors, okay? So the delta R between these two, I'm going to do R2 minus R1. So it's going to be 90 minus 77 is 13I. 75 minus 59 is 16J. So this is the separation vector. And the magnitude of the separation vector is going to be the distance between the two projectiles. Okay? So the answer is going to be square root of 13 squared plus 16 squared. .6 meters. So it's going to be about 21 meters. All right, so I would consider that a slightly more advanced projectile motion problem. It involves two projectiles. It involves thinking about this two-dimensionally. Let's do another example. What if I went with that projectile number 2 again? So that, remember, that projectile was launched from 80 meters up in the air. and it was launched horizontally at 90 meters per second. Like that. So we had an x of t for this projectile, and let me refer to the previous page, was 90t, and the y of t was 80 minus 5t. 90t and y of t is 80 minus 5t. So my question is, how fast is it going just before hitting the ground? How fast is this projectile going just before hitting the ground? Now, if you took my class last year, you know that you could use conservation of energy. You could say, well, the projectile starts out with gravitational potential energy and kinetic energy, and just before it hits the ground, it has only kinetic energy, so you could set up a conservation of energy equation and solve it. Yes, it's minus 5t squared. Thank you very much. But I want to do this with oh no, I've been invaded by former students. Hello, Elena. Get back to work, doing whatever you're supposed to do. But hello. Really creepy story. I can tell you a really creepy story about Elena and Chris. They showed up at my doorstep. I got a knock on my door at like 8:30 at night, and it was Chris and Elena. And I think they were thinking that I was going to be like all awkward and stuff and be like, oh, what are you guys doing here? But I decided to counter that by just saying, oh, do you guys want to come in and play Chinese checkers with me? And so we played Chinese checkers. And I won. And then they went home in shame after being defeated in Chinese checkers. Okay. It's actually not that impressive because it's pretty easy to find where an adult lives if you just go into Google and you type person's name, address, and you can find it, okay? It's super easy. Can figure out where Dr. O'Connor lives very easily. Okay. So what I'm going to do, first of all, is I'm going to figure out when does it hit the ground. So what is the y-coordinate when it hits the ground? The y-coordinate is 0, okay? So I set this equal to 0. And so you just are going to solve for time. So I have 80 equals 5t squared. So that says that t squared equals 16. And that says that t equals 4 seconds. Okay. All right. So the impact is going to happen 4 seconds after the launch. But we want to know how fast is it going. So that has to do with velocity. So what I'm going to do is I'm going to calculate dx dt, the derivative of the x-coordinate, evaluated at 4 seconds. Okay? So the derivative evaluated at 4 seconds. So that means take the derivative and then plug in t equals 4 seconds afterwards. And so you take the derivative of that and you evaluate it at 4 seconds. You just get 90 meters per second. And then if you were to do dy dt, evaluated at 4 seconds, you are going to get negative 40 meters per second. All right? So this is the x component of the velocity. This is the y component of the velocity. But we want to know how fast. How fast is speed? And if you recall from our second lesson, speed is the magnitude of the velocity vector, which means do the Pythagorean theorem. So the speed it's going just before hitting the ground is going to be square root of 90 squared plus 40 squared. Which is about 98 meters per second, 98.5 meters per second. Okay? So there you have it. All right, we're going to move to another concept that I think is kind of interesting. It's called the concept of trajectory. So trajectory is, if we look at these equations of projectile motion, they have position as a function of time and elevation as a function of time. The trajectory is the elevation as a function of x. Okay? So it's expressing the elevation in terms of a different variable. So what we have to do, and so when I solve this, I'm going to go ahead and say that it's launched from x naught equals 0. Okay? So if you do that, your x of t equation is just going to be vx naught times time. Okay? Because if x naught equals 0, then this first part goes away. All right? So we have time equals x over vx naught. All right? Then we are going to go to our y of t equation, which is this, and we are going to plug in the expression for time that we just got. So I have y naught plus vy naught times, and instead of time, I'm going to put in x over vx naught. And then I have minus 1/2 gt squared, but instead of time, I'm going to put in x over vx naught. All right? So I replaced time with position. Now all we have to do is simplify it. So we have y naught plus vy naught over vx naught times x minus g over 2 vx naught squared times x squared. So this is a parabola. Y is a function of x. It's a concave down parabola, and that would be the shape of the path of the projectile. We can simplify this even further if we use the fact that vy naught and vx naught are given by these expressions. So in particular, vy naught over vx naught, that's like opposite over adjacent, which is just tangent of theta. Okay? So we have y naught plus tangent of theta times x. All right? Keep in mind this x is not inside. It's not an argument of tangent. It's just you calculate tangent of theta, and then whatever number you get, you then multiply by x. Minus g over 2 v naught squared cosine squared of theta times x squared. So this is called the trajectory function, and it's quite useful. All right? This is the trajectory for projectile motion. So the trajectory, it's completely general. Anytime you have motion, it doesn't necessarily have to be projectile motion. You could have a trajectory. The trajectory, and the other thing about trajectory is it's not necessarily a function. You know how functions have to satisfy the vertical line test, but you could have a trajectory where something goes out and then it curls around and it comes back. So that would not be a function. It would so your trajectory might not even be an actual function. It might not satisfy the vertical line test. However, if you describe the motion in terms of x of t and y of t, you can only be at one position at a given time. So these two will always be functions, but your trajectory might not be a function. All right, so we can use this to solve kind of an interesting problem, I think, which is, okay, so what if we launched that projectile, that same projectile that we've been working with this entire lesson, which is the 100 meter per second projectile that's launched at 40 degrees above the horizontal. Only we're not going to have this projectile launched across a level surface. We're going to have it launched across a sloped surface. Okay? So here is the surface. So it's launched basically up a hill. Or you could have it launched down a hill, something like that. And so the projectile is going to go like that, and it's going to land right there. And I want to know, what is the x-coordinate of where it lands? Okay? So to describe the hill, we need a function that describes the shape of that hill. This is a linear hill. So I'm going to define a hill function. Hill, what is the elevation of the hill as a function of x? Okay, and because it's a linear shaped hill, it's going to be 0.5x. All right. So we have that, and then we want the y of x of the projectile itself. Okay, so the projectile is launched from the origin, so y naught is 0. It's launched at an angle of 40 degrees. There's a good question, which is, why is it 0.5? So that would just depend on the steepness of the hill. I'm saying that in this particular problem, the hill has a slope of 0.5. Okay, so its rise over run is 0.5. So the steeper the hill is, the bigger that number is going to be. All right. So we have tangent of 40 times x minus g, which is 10, over 2 v naught squared, so 100 squared, cosine squared of theta, which is 40, times x squared. So let me crunch the numbers here. So this is 0.84x. Okay. 10 over 2 squared over cosine of 40. So we have minus 0.00085 x squared. Okay. Another good question, is it 40 degrees over the hill or 40 degrees over flat ground? It's 40 degrees above the horizontal. Okay, so that would be relative to flat ground. Although that's a good idea for a question, for testing the understanding. I'm going to work on that. So how do we tell when it hits the hill? It's basically a collision. It's a collision between the trajectory function and the hill function. So we just want to set these two functions equal to each other. So we have 0.5x equals 0.84x minus 0.00085x squared. I'm going to add this over to the other side, and I'm going to subtract that over. So we have 0.34x equals 0.00085x squared. Then I'm going to divide both sides by that. So we get 0.34 divided by 0.00085 is 400. So we have x squared equals 400x. And then, now here's the thing. We actually have two solutions because the projectile is launched from the hill. So when x equals 0, we've made contact with the hill. But then the second collision is when x is not equal to 0. So we can divide both sides by x. And we get that the collision will happen 400 meters downrange from where it started. Now, one of the things that's interesting about this is I chose a hill shape that you could solve easily. Okay? I chose a hill shape where you get an equation that is solvable using algebra. Okay? I could just as easily write a hill function that is not solvable algebraically and it only is solvable with a computer. Okay? So for example, what if I had like rolling hills? In this case, you would have a launch, right? And it's going to go like this. So you have, so your hill function would maybe be like sine of x or something like that. And so you're trying to solve the equation sine of x equals a parabola. So that's an equation you can't solve algebraically. You would need a computer. Okay. I want to put another thought into your head, which is, what if you wanted to design a game? You know, some game physics. This type of problem always makes me think of the game Worms. Has anyone ever played the game Worms? It's an excellent video game. It's basically you control worms with bazookas, and you try to launch your bazooka and get all of the other worms on the other team. So it's like 5v5, 5 worms versus 5 worms, and you're launching projectiles at each other. It's good fun. Yeah, so anyways, some of the game physics for worms would be like you could have, and you can have different weapons. Like you have a weapon that might bounce off the hill. So how do you get it to bounce off the hill realistically? Well, you would find the point of contact, and then you would figure out the slope. And then based on that slope, you could figure out what is the velocity that it reflects at. So you could have it go doink, doink, like that or something. So the game physics is like 100%. The game physics of worms is 100% projectile motion. It's pretty cool. All right. So I think that's my lesson. So we're going to jump over to the Zoom room, and I will answer any other questions you have. So thank you for watching.